afternoon, guys. That was good. Oh, doing better. All right, we have tonight, and then you have an exam on Wednesday. So, what we are going to do today is finish up this material for the exam. I'm going to talk about the exam, and then I will finish up anything that you want to know about nomenclature or anything else that would be on the exam that I can help you with. Probably will be done early, so that's a good thing. And need you to sign in. Somebody's here from my 8 o'clock class. Okay, I'm going to send this to, actually, let me just bring it to you to confuse them. Sure, you come sign it for me. I think I left you off today when I went through. Guys, I want to talk to you real quickly about absences. There was a question that or comment that was made, something to the effect of, someone made the comment, well, I've only missed 4 classes, and I thought to myself, that's not good. That would be me, if someone missed 4 absences, I would put a mark on their 5th week check-in saying you've had too many absences. That to me is way too many. 1 or 2 is acceptable at this point. But if you've already had 4 and we haven't even gotten to the halfway point in the semester, that's concerning me. Some of you are there. Some of you are 3 absences or 4 absences. You may not be here. Chances are you're not. But if you are here and you've already had 4 absences, then you really need to decide if this is really where you need to be between 450 and 650 on Monday and Wednesday. Because remember, I believe, is it 5 absences and your grade gets lowered. That means if you're just eking by with a D at the end of the semester and you have 5 or more, then your grade gets dropped lower. That means if you have a C going in to you're done, but you had 5 absences, you end up with a D. There is no excused absence, period. Okay? I've never kept up with attendance before, but I've also never had videos before. And that's why we're doing that, because yes, it would be very easy for you to just not come. So I understand that. But you did sign up for the class not as a quote video class. Now, is that to say that in the future I might teach this class as a kind of a flip where maybe we'd come once a week instead of twice a week and you'd watch the videos? Possibly I may do that, but yours is not. Yours is expected to be here every day. With the 5th week check-in comment, let me say this if you're not familiar with that. The 5th week check-in is a across the board, all freshmen and sophomore in 100, actually I think it's anybody in a 100 or 200 level class. I may be wrong on that. It may just be freshmen and sophomore in 100 or 200 level classes. We will make a mark or make it known. We do an assessment of you guys in the sense that I make a mark if you've had, and like I said, for me, it typically is 3 or more absences at this point. I will say you have had excessive absences, or if you have a D or F right now. Now, the right now means without the ion quiz, and I did not have the ion quiz graded, but I'm glad I didn't, because that actually can be a really super artificial inflation on your grade at this point, because the fact that it is 10 extra credit points. And so it probably, your grade without the ion quiz right now is a better gauge of where you are. There are some of you who have a D or F right now, and you need to pay attention. You know your grades. They're all on Blackboard. You know your grade. So it's up to date on Blackboard. So if you have a D or F right now, again, you've got to test Wednesday. After your test and your homework on Wednesday, if you still have a D or F in this class, I would really encourage you to talk to me and consider maybe taking a bi-term and dropping chemistry, because maybe life is too busy right now and you need to focus on other things. And I understand that. And so let's talk. If you still have a D or F after Wednesday, let's talk, because we'll want to decide that. I think the last day to drop with a W is October 11th. And you will, it's actually the day, it's the Wednesday the 11th is the last day to drop the class, and then that next Monday is your test 3. So this after test 2 is the deciding factor. All right, so after test 2. So if you have any questions, let me know, but next Monday, see me and you'll know your grade by then, and we'll look at it. I have tests with me for test 1 for us to go over. Those of you that have not, if we do that tonight, that's great. If we want to wait, I will bring them back one more time, and if I will make you see me Wednesday after your exam. So if you have not seen me before then, I will say take this and look at it. You have to look at it. You have to look at your test sometime, because you may have points on there that you get, and so I want you to get those points if you have them on there. Any questions on grades? Test is still downstairs. That's where your test will be until otherwise noted. So and we'll talk more about the test. So we ready to get started on this? Grab a periodic table. You need your periodic table out. All right, let's talk about, I want to kind of give you a big picture of where we're going right now, and then we're going to come back and actually write down some notes. Electronegativity is where we're starting, and I'm going to tell you right now, what we're talking about today actually is going to be used more when we get into the organic chemistry portion of this class, which is going to be after Halloween. So we're talking about it today because we've just come through the trends, and so we're going to talk about it today. We're going to look at it today. The reason we're also dealing with it today is because we've just gotten through Lewis structures, which also plays a part in this, but it will actually be used more when we get into the organic portion. So you're going to have to kind of keep that in the back of your mind. This is very little of this is going to be on this exam. What this will help you with, though, will be on your exam, the last 5th exam. Okay, so it's kind of going to be used both. That's one of the joys of chemistry, I think. I know it's not like joyful to you probably, but one of the good things about chemistry, I think, is that it gets used. What we've done gets used, and I like that. I am not a fan of a class that I take and I learn it for a test and I can forget it and it was like pointless. Why did I learn that? I want to use what I learn. If I'm going to spend my time learning it, I want to use it, and that I do think chemistry does that. A reminder of what electronegativity is. Electronegativity is a measure of the atom's attraction for shared electrons in a molecule or polyatomic ion. In other words, it is how tightly an atom holds on to or pulls shared electrons to itself. Who is the most electronegative atom on the entire periodic table? Fluorine. Who's second most? Oxygen. Good. Okay. Guys, I want to tell you all something. I appreciate you all talking to me. The first day of classes, the 8 o'clock class did better than you all in talking to me, which was odd. Since then, they are just like bumps on logs, and it's so hard to teach them. I mean, I feel like I just drag through that class because they won't talk. It's so much nicer to have people that talk. So thank you all. Thank you for talking. It just makes it so much nicer to have that interaction. Okay, so that means if oxygen's the second most, fluorine is the most, tell me if oxygen is with fluorine, who pulls those electrons most often? If oxygen's with fluorine, who pulls them most often? Fluorine. But if oxygen is in a polyatomic ion, like you see it a lot, carbonate, sulfate, phosphate, oxalate, all those, then who's getting the electrons most often? Oxygen. Okay? That is a huge thing, just remembering that. That's huge. Now, think about that scenario where you have oxygen. It's pulling the electrons more to it. And let's just go to water. Let's just take water. You've seen me do this a lot, so let's just take water. You've got your hydrogen bonded to oxygen, bonded to hydrogen. Who is hanging on? Who are the electrons hanging out with most? Oxygen. So is oxygen more negative? In essence, yes. The electrons are hanging out with it more often, so it makes it not negative in the sense that it gained electrons, but it's more negative, and hydrogen is more positive. That difference in electronegativity causes this to be more negative and each of these to be more positive, which makes then this bond be called a dipole, which is basically a separation of charge. It's not a true charge per se. We don't say hydrogen's +1 and oxygen's -2, but we do say oxygen is more negative and hydrogen is more positive. Any of those scenarios where you have a great difference in electronegativity, you will have a dipole. You will have a separation of charges basically because the electrons are hanging out with the more electronegative one and not hanging out with the more positive one. And that makes the more or the less electronegative one more positive, the more electronegative one, I said that really bad, more negative though. That is also called, if it's a dipole, it's also called a polar bond. Now if there's a huge difference in electronegativity, meaning like a metal and a nonmetal, then that's strictly an ionic compound. In that scenario, is it a sharing of electrons or a true transfer? That's a transfer. That's just a straight transfer. So that's an ionic compound. So that's different than this polar bond. This is still sharing, just not sharing equally. What if they share totally equally? Who is the only one that you know of that shares totally equally? There are 7 of them. The diatomic molecules. The diatomic molecules are the only atoms that share electrons equally in that sharing relationship. Why? Because they both have the same electronegativity. Is that to say they're the only ones? No, but that's the only ones you knew as of this point. You didn't know anything besides those today, until today. So all of what I've said is basically on here. Let's write it down now. So if the same or very close electronegativity, and there's a mistake here. This word should not be atoms, it should be electrons. So if we have the same or very close electronegativity, then electrons are equally shared, and we say the bond is nonpolar. The bond is nonpolar. And nonpolar bonds are going to be all the diatomic elements. All diatomic elements have nonpolar bonds. And there's another nonpolar bond that's going to come in to play when we get into the organic. The CH bond is also nonpolar. How do you know that it's nonpolar? Because the electronegativity difference is less than 0.5. You don't necessarily have to write that down. You may if you want. It's written already on the paper, and it's also written right here in the next statement. If the electronegativity difference is 0.5 or greater, the bond is said to be polar. And electrons are not being equally shared. Polar bonds are dipoles. Polar bonds are dipoles, meaning they have that difference in who the electrons hang out with the most. They've got that little bit of a separation of charge because of the unequal sharing of the electrons. If the electronegativity difference is greater than 1.9, the bond is said to be ionic, and obviously this is an ionic bond. This is a metal plus a nonmetal. That's when you will have this ionic bond. So ionic compounds will have ionic bonds. Diatomic elements and the carbon-hydrogen bond is a nonpolar bond. So who fits into this category? Most molecular compounds have polar bonds. Not all, and you might not even put most. You might just change that to many, because I don't want you to think, well, they all do. As soon as you say most, it's like, well, they all do. No, many. Many molecular compounds have polar bonds. So if you think of water, what did we say that is? Is that a polar bond between hydrogen and oxygen? Is that a polar bond? Yes. What's the bond between carbon and oxygen and carbon dioxide? Look at the electronegativity difference. Find those on your periodic table. What's carbon? 2.55. Oxygen? So is that greater than? Good. So greater than 0.5. So that is definitely going to be a polar bond. Methane was a compound that I had you draw in our Lewis structures. Do you remember what methane is, the formula? It's on your notes. CH4. That means C in the middle and then the 4 hydrogens on all 4 sides. Those bonds are all nonpolar. So that whole molecule, and we're going to get to that in just a minute, is nonpolar. The whole molecule is a nonpolar molecule because all the bonds are nonpolar bonds. The little table here at the bottom should help as far as helping you remember the difference. Someone asked me today, what if it is 1.9? What is it? I'm hoping you're not going to have any that you have to make that guess. I'm not going to try to trick you up. In fact, there's some of these at the bottom I'm going to take out because they are tricky. But if it's right at 0.5 or it's 1.9, I'm going to try not to give that to you because then it goes into the electronegativities that I have given you on your periodic table are one way of measuring electronegativity. There's another way, and then it's all gets too confusing. And so I'm going to try to stay away from the extremes, and we're going to deal in the middle. So why do we do this at all? Who cares whether they're polar or nonpolar bonds? That's what you've been saying all semester, right? Who cares about chemistry? Well, who cares? Here's why it's important in a big picture scenario. There is a saying, like dissolves like. You may not have ever heard that before. Has anybody heard that before? Anybody at all ever heard like dissolves like? Thank you. So somebody's heard that before. What does that mean? That means if a substance is like another substance, it will dissolve it. Okay? If a substance is chemically like another substance, it will dissolve it. Knowing that statement now, what makes substances that are alike is their polarity. Not just the polarity of the bond, but the polarity of the entire molecule. And so what we're going to investigate as we go through that organic section, and we're starting right now, is we can actually, by understanding just that phrase, like dissolves like, we can pretty much figure out things that are like water and things that are like oil. Because we automatically know oil and water don't mix, correct? We all know that, right? Oil and water don't mix. That means they are not alike. Which means if it's all based on polarity, one of those is polar and one of those is nonpolar. So then, taking that knowledge, when we figure out which one of those is polar, we'll automatically know the other one's nonpolar. Then we can step back and just start naming off substances. And we can even do that ahead of time. For instance, oil and gasoline. Do they mix? Now I realize I'm talking to people that may not know that answer, but somebody might. Do oil and gasoline mix? Does anybody know that answer? Incorrect guess. They do. That's okay. Thank you for talking. Oil and gasoline mix. What about oil-based paint? Have you all ever painted with oil-based paint? Nope. Maybe? Every semester I say to the students, what do you people do? I'm like, do you do anything besides get on that stupid phone? I mean, get rid of the phone for a week and have a life. You're missing out on real experiences. Go paint a wall, okay? Go mix things up. All right, so let's go backwards here. A little lesson on the side. Oil-based paint, when you go to Lowe's and you say, okay, I need some paint, and they're going to ask you, do you want latex or do you want oil? Latex means water-based. That means it's like water somewhat, right? And oil-based paint, they're going to say, if you're going to get oil-based paint, you have to have a solvent that's going to help you clean up your brushes, called paint thinner. Okay? Paint thinner then must be like oil-based paint if it cleans the brushes. Which then, let's go a step further. I have told you that gasoline will also clean those brushes for you, or diesel fuel. So all of those then, gasoline, diesel fuel, oil-based paint, paint thinner, are all alike. Yes? Now, do you think that water and gasoline mix? No. No. Have you ever heard anybody say you might have water in your gas? Okay? And it doesn't run well when you do because they don't mix. Okay? So already then you've got a category that you're thinking, okay, these are all alike, so they're like each other. Now we still don't know which one's which, polar or nonpolar, but we know those are all alike. Then you start looking at your water and say, what does dissolve in water? Sodium chloride dissolves in water. Well, sodium chloride is an ionic compound. So that means sodium chloride is an ionic compound, and that is an ionic bond. That means it dissolves in water. But water's not ionic. We all know that. What do you think water might be then if it would dissolve an ionic compound? Would it be nonpolar or would it be polar? Polar. Water is polar. Think about the steps we're taking. We went nonpolar, no difference in electronegativity. Polar had a difference. Ionic was a great difference. Obviously, we would need to be close to the great difference if we're going to make it dissolve. I'm hoping you follow that thought process. Okay? So, let's decide then, how can you tell, without going through all kinds of examples, how can you tell if a bond, or we already know how to tell if a bond is polar, but now we're going to the molecule. Just the bond alone doesn't tell you like dissolves like. It's the polarity of the molecule that tells you like dissolves like. So here's the rules. A molecule with no polar bonds is a nonpolar molecule. A molecule with one polar bond, only one polar bond, is a polar molecule. We've already talked about a dipole, and you could go ahead and put here polar bond is a dipole, just to help you remember it. We wrote it up at the top too. So we know now if it has all nonpolar bonds, it's a nonpolar molecule. So methane, CH, all what? Nonpolar bonds, so methane is nonpolar. Would methane dissolve in other nonpolar substances? Yes, methane would dissolve in nonpolar substances. You already told me earlier, somebody said water was polar. They're correct, water is polar. So would methane dissolve in water? No. Okay, if you've already decided that water is polar, I'm going to show you why water is polar in a minute, but if you've already decided that and you're correct, water is polar, then automatically what does that tell you? Oil, paint thinner, gasoline, nonpolar. So will methane dissolve in those? Yes. Okay. All right. If the molecule, here's the question though. This was one polar bond. This was no polar bonds. What if it has more than one? If the molecule has more than one polar bond, then you must look at the shape of the molecule, which is why we're doing this now, because we've just finished with Lewis structures. So here's how you know. You have to look at the shape. And I'm giving you simple ones. I'm going to tell you that right now because these can be really confusing. If the dipoles, or the difference in charge, or the polar bonds, however you want to call them, if those go in the same, and I'm going to add a word, general direction, same general direction, the molecule is polar. But this is the real key. If the dipoles go in opposite directions, the molecule is nonpolar. So if they go in truly opposite directions, the molecule is nonpolar. So we're going to look at some examples down here, and I'm actually going to take the CH2F2 out, and I'm going to take the HCN out. I'm going to take those two out. We're not even going to worry about them. And let's do these examples. This is enough for right now for what we're doing. I'm going to basically explain to you, I've given you what these are. I'm going to explain why they are what they are. Okay? HCl. What is H's electronegativity? What is Cl? Is it greater than 0.5? Yes. So it is greater than a 0.5 difference. That means that this bond, and you can draw it, I think you all should see that that truly is how it's drawn. Does everybody get that? That shouldn't be new to you right there. Who gets the electrons hanging around it more often? Chlorine. Now, the way we can draw dipoles is like this, a positive arrow on one end and then pointing to the negative. Now, your book and the chart that I'm using today actually uses a sigma to show this, but this is a fast, easy way to do it. What this is saying is that this is one polar bond. Chlorine gets the electrons more often because it's the more electronegative. It has one polar bond, so what is the whole thing? Polar. Because it only has one polar bond. This one's an easy one. It has one polar bond. So you could put one polar bond. That means the whole molecule is polar. The whole molecule. This row, the molecule. This is the polarity of the molecule. The molecule is polar because it has one polar bond. Then we go to water. You've already told me water is polar, and you did that with your process of basically elimination of if it's going to dissolve ionic substances, then it couldn't be nonpolar because that's too far away, so it must be polar, and you're correct. Then that's great thinking. Let's look at the rules of why it's polar. Every time I've drawn water, I have drawn it kind of straight out, but that's not really the shape of water. What's the shape of water? It's bent. Water's bent, and that's why. That fact that it's bent is what makes it polar. So I'm going to draw it now bent. And you have to remember this is three-dimensional. It's supposed to be three-dimensional, okay? So that is bent water. That's water bent. And if you realize, again, I was trying to be kind of general on my wording here. I said if the dipoles go in the same general direction, but then I was real adamant about if they go in opposite, then it's such and such. But if they're kind of the same, and here's why I did that. Who gets the electrons most often? Oxygen. So basically, this is the path of our dipole. Meaning, are they both going north? Not really. One of them's going northwest, one's going northeast. You see what I'm saying? But then look at it. Are they opposite? They're definitely not opposite. They're definitely not opposite. Are they going in the same general direction? Yes. So now that's why Water's polar. That's why. If these were going in opposite directions, then they would, in essence, cancel each other out. But the fact that they're going both toward oxygen, both in the same general direction, that's what makes the entire molecule polar. So water is polar. That is huge. And in fact, we're going to talk a lot more about this when we get to this back in the organic section. But water is the solvent that everything is tested in. Because you immediately test it in water. Tomorrow in Glasgow, I'm doing a 106 lab, and they have an unknown liquid. And their unknown liquid is going to be tested in water. That's one of the physical things they're going to do. They're going to test its solubility in water. Because immediately, if you know it's soluble in water, what does that immediately tell you? It's polar. And that's immediate. You can just, okay, we can get rid of this whole class of compounds, and now we can identify it based on that one thing, and then more testing. But it's a huge benefit to know whether it will dissolve in water, because water is such a good polar solvent. It's the standard polar solvent. Carbon tetrachloride is actually the standard nonpolar solvent. But why is it nonpolar? Because if you draw carbon tetrachloride, and folks, I'm drawing these quickly. If you don't quickly see why they have this shape, then go later on your own and draw these out following the rules. But that is carbon tetrachloride. What is the difference in electronegativity between carbon and chlorine? Is it greater than 0.5? Yes. Who gets the electrons more often? Chlorine. No, it's chlorine. So basically, this is what you're dealing with here. All over the place. Everybody's going to chlorine, right? You've got all the electrons are being pulled by chlorine. But what did we say? If they're going in the same general direction, it's polar, but if they're going in opposite directions, it's... Now think about this for a minute. Imagine, if you will, that I have a post up here in the middle of the room, and it's a big fence post. And I pick 4 of you, and there's 4 ropes attached to this. And I say, make this post stand up straight. How would you do it? How would you get that post to stand up straight? There's 4 ropes attached to it in the middle. You got it. 4 people. Now, can the one up here and the one here be pulling too hard? Harder, I mean, than that? No. What do you have to do? Equal. You each would have to be pulling equally. And if you each pulled with equal force, that post would stand straight up. And it would not fall because you each are holding it with, that's what then the whole thing is nonpolar. That's why the whole thing is nonpolar, because it's equal but opposite. And so they're basically, the whole thing is nonpolar. There's no pull that's greater any one direction. The whole thing is nonpolar. CO2. If you remember, CO2 had 2 double bonds. Again, go back and do these if you don't remember. This was CO2. Who is more electronegative? So basically what's happening is this. Yes? So keep going. Why do I call it a nonpolar molecule? Because those polar bonds are going in opposite directions. Now then, take my post and just put 2 people. And they can hold it up because they're pulling it, the 2 people. Does that make sense? Kind of like an equal tug of war where nobody wins. That's what this is. All right? On your test, you will have some compounds that I will ask you to tell me if the bond is polar or if the whole thing is polar. You have a periodic table. You don't have to memorize electronegativities, although most of them you're going to know just by kind of practicing a little bit. The other thing I would encourage you to do is go back to two things. Go back to your Lewis structure page that you've already done and just look at those and start to decide what those would be, what those bonds would be. Then do some more Lewis structures, maybe the Lewis structures you did on sapling. Decide, would those bonds be polar or nonpolar, or would the whole molecule be polar or nonpolar? Just kind of practice that a little bit with some other examples. And I'm asking you to do the same thing with the next comment, or the next concept rather, which is intermolecular forces. Again, this is going to play more of a part in what we do with the organic section, but it goes right along with what we've been talking about already with our polar bonds, and that's why it's included right here. No, this is on the test. All this is test. This is it. This is the last page of test. Intermolecular forces are the attractive forces that exist between molecules. And let me explain this. And I didn't bring my water inside today, unfortunately. But imagine that jar of water. That's not one molecule of water, is it? That's lots of molecules of water. And those molecules of water are interacting with each other. This sounds dumb, but imagine it. If the molecules did not interact with each other, or let's go backwards, do you think the boiling point or the freezing point or even the state of the substance, does that make a difference in how the molecules interact with each other? Do you think that makes a difference? And it does. If the molecules have great interactions or very strong interactions, then they would have a higher boiling point. If they don't have great interactions or strong interactions, they would have low boiling points because they don't care if they stick to each other. So it's kind of like you with people you know. You have those strong intermolecular forces with some people you know, and then you have weak intermolecular forces with others, and that's okay. That's great to have a good mix of people. You've got acquaintances and you've got best friends, right? That's okay. That's the same kind of thing. All molecular compounds have intermolecular forces. And they all have either one of these or two of these or all three of these. There are only three that we're going to deal with. There's just the three intermolecular forces that are listed on this page. They're London dispersion forces, also called van der Waals forces, dipole-dipole interactions, and hydrogen bonding is the last intermolecular force. Again, I've already said this, the three different types of intermolecular forces, they're listed here in increasing strength. And the strength of these forces determines whether a compound has a high or low melting or boiling point and its state at a given temperature. Now, before we even look at the different forces, I want to take that comment at the top there. Within a group, in other words, if we were just looking at compounds that have London dispersion forces, or if we're just looking at compounds that have dipole-dipole, which would then also have London, or if we're just looking at hydrogen bonding, within the group, the larger the molecule, the stronger the intermolecular forces. So I'm going to give you two examples. I'm actually going to use this example, and it should be up here instead of down there. Using this example, the larger the molecule, the stronger the intermolecular forces. Which of those has the greater intermolecular forces? I don't care which ones it has. Just tell me which one of these has bigger intermolecular forces based on that statement. C12H22O11. Why? It's bigger. And some of you are like, well, why? How do you know it's bigger? Obviously it's bigger. It's got 12 carbons compared to 1 carbon. That in itself makes it bigger. The more atoms makes it bigger. Okay? So this would be the larger. This would be the smaller. So this is really not an example of only London. This really goes up there, and I should have put it up there. So now then, so you understand the larger the molecule, the greater any of the forces would be. But now let's look at the three forces. So London dispersion forces, sometimes they're called LDF. You see that written, LDF. First of all covalent or molecular compounds, that means the same thing. All covalent or molecular molecules have London dispersion forces. In other words, anybody who shares electrons has London dispersion forces. Anybody. If they share electrons, they have London dispersion forces. Which means then, if I give you these two examples, and I'm going to tell you who these are. This is methane. This is propane. If you have atmos energy, you have methane. If you have a propane tank, you have propane. If you have a gas grill that's not hot wired, I say hot wired, isn't hardwired to your house, then you probably are burning propane in your gas grill. All kinds of things I could ask you about this. First of all, are these polar or nonpolar? How do you know that? Because they're all CH. It doesn't matter that you don't know how this goes together. It doesn't matter. But you do know it has only C and H. Now, I couldn't ask you about these because it makes a difference how these are put together. But here, it doesn't matter how these are put together. They're just C and H. The fact that this has O in it, yeah, that matters because it matters how it's put together. But the fact that these only have C and H, that definitely means they are nonpolar because it's only nonpolar bonds. Now, just so you know, this is something you're going to get to later. You know what CH4 looks like. You don't know what this looks like, so I'm going to show you. Anytime you have a series of carbons, it's actually the carbons that are hooked together. So that's propane. You're not going to have to draw that today. That's later, not today. But I'm just showing you. So now you know they're all hooked together. Now you should definitely be able to tell me if I ask you this, which isn't on this page, it's the previous page, is that polar or nonpolar? You should be able to say it's nonpolar. Okay? By seeing what it looks like. And if I drew these, you should be able to tell me also what they are, polar or nonpolar, based on what they look like. But that wasn't exactly where we're going. Now my question is, do those CH4 and C3H8, do they both have London dispersion forces? Yes. Why? Because they're sharing electrons. So they both have London. They both have London dispersion forces. Now my question is, who has the greater intermolecular forces? Propane does. C3H8 is the greater. That's the higher intermolecular forces, and IL means intermolecular. So propane would be the higher intermolecular forces. Why? Because it's bigger. That's why. That's why. What is a dipole? How can I say another word, or what's another way I could say dipole? A polar bond. So what you are looking for to know if you have a dipole is you look for a polar bond. If you have a polar bond, then you have a dipole. Dipole-dipole interactions are the next strongest intermolecular force. If you have dipole-dipole, you also have London dispersion, because what are polar bonds? Just electrons being shared unequally, but they're still being shared. So if you have dipole-dipole, you also have London dispersion. Formaldehyde, which is this CH2O, this really is what that looks like, just so you know. That really is what it looks like. First of all, when you're looking at this, you see the C and the H. All that area is nonpolar. Do you agree? But what is CO? That's polar. Isn't oxygen more negative than carbon when they're bonded? Oxygen hangs on to the electrons more often than carbon does. Your picture shows this, like I said, with the sigma positive, sigma negative, same kind of thing I'm drawing here. That is your dipole. And what happens is you get the dipole-dipole interaction. So in essence, it's as if that more negative oxygen is being attracted to that more positive carbon on the next molecule, and they're just all interacting with each other and causing that to be stronger.
Can you repeat that just one more time, like why it's a dipole?
Because it has a greater electronegativity difference than 0.5. It's a polar bond. Okay? Again, if it has dipole-dipole, it has dipole-dipole, and it has London. If it has one, it has both of these. Go ahead.
So in that one, are the hydrogens basically just like neutral, like tagging along?
The hydrogen and the carbon bond is nonpolar. So it's not, so hydrogen's not involved in the interaction. Now, does it provide London dispersion forces? Yes. But as far as the dipole part of it, no. Like you said, it's just kind of out there. It's just kind of trailing along. But what is actually interacting is the carbon and the oxygen between the carbon and oxygen of the next. Okay? Hydrogen bonding is very specific. Hydrogen bonding is actually only going to occur, it's first of all, it's the strongest intermolecular force. It is the strongest intermolecular force, but it only occurs with HO, HN, and HF bonds. In other words, you have to have an HN, an HF, or an HO. If you don't have an O with an H bonded, it has to be bonded. O bonded to H bonded to F, H bonded to N, then you don't have hydrogen bonding. You still could have a dipole, and you could still have London dispersion, but you would not have or hydrogen bonding. Now, if you have hydrogen bonding, what do you also have? You have dipole-dipole and London dispersion forces. And somebody's saying to themselves, well, how can you have dipole-dipole? Because look at the difference between H and O in their electronegativity. Is it a polar bond? Yes. So is that a dipole? Yes. Is that a dipole? Yes. Is this a dipole? Yes. So each one of these is a dipole, but it also provides hydrogen bonding. So if you have hydrogen bonding, you also have dipole-dipole, and you also have London. And so this is the strongest intermolecular force. This little table is a summary of what I've just said. And that shows you some examples. It shows you with who will do hydrogen bonding. It's just like a quick little note. What I would strongly encourage you to do is go back to those Lewis structures that you've drawn or that you've seen on sapling and make sure that you can basically take those not only and draw them, but then look back at them and say, do they have polar bonds or nonpolar bonds? Is the whole thing polar or nonpolar? And what type of intermolecular forces are there? And if you can do that, there's like 2 or 3 questions on this exam that's about this, and you're like, I got it. That'll be easy to you because you've gotten that. Go ahead.
So any polar molecule has dipole-dipole?
No. Oh, yes. I'm sorry. Yes. Any polar... Yes, you said any polar molecule has dipole-dipole. Yes, because a polar molecule has either one polar bond or more than one. So yes, that's okay to say that. I try not to say things like that, but that is correct.
So if it has a hydrogen bond, would it be also dipole-dipole and London?
Yes. Exactly. And this basically what you can look at is, and you can write it however you want to, if you have this, I know I've seen those little things you all do, that you did this stuff in school. There's a little chart that's like the big circle, and then this would be inside the big circle, and then a Venn diagram. Is that what that is? In other words, hydrogen bonding includes both of these. Dipole-dipole includes London. So in other words, you could draw a big circle. You know what I'm doing.
So London can stand alone by itself.
London can stand alone by itself. That's the only one. Because if it's dipole, it's going to have London. If it's hydrogen bonding, it's got all three. Okay? Make sense or not? All right, wake up back there in the back. He is snoozing away, isn't he? Hello! Welcome to chemistry. What were you dreaming about? Don't want to know, huh? You dress so nice, but then you sleep in class. That's not good. All righty, so I'm ready to talk about the test. Let's talk about the test. Is it about the test or about this? Okay, guys, wait just a minute. She's got a question about this before I talk about the test. Go ahead.
Whenever you draw the newest features, as you go back, will you ask if it's like one of the, like on the top one in stage 4, will you ask like if C is polar, non-polar, or just like H, or like if
I would say the bond. Is the CH bond polar or nonpolar? Then I could say, is the molecule polar or nonpolar?
as in H or C?
No.
Like,
I'm not quite following what you're asking. Let me say how I may ask it, because I can't guarantee I'm going to ask this, but this could be a logical way to ask the question about polarity. In methane, is the CH bond polar or nonpolar? That'd be one question. And the answer is it's nonpolar. Is the methane molecule polar or nonpolar?
what's the difference between the molecule?
Because the molecule is made up of 4 bonds. So it's kind of like saying, what's the Vesper geometrical shape of methane? I'm not asking you what's the Vesper geometrical shape around hydrogen. I'm saying what's the whole thing. So if I say what's the polarity of the molecule, I'm talking about the whole thing. If I'm asking you specifically about a bond, then I'll say the bond. I'll say the elements of the bond. So in other words, here I could say what is the polarity of the CH bond, and I would write C-H bond. That's nonpolar. What is the polarity of the methane molecule? Well, it's also nonpolar because all those are nonpolar. But if I went back to the previous page, that could be a different question. For instance, here I could say something like on carbon tetrachloride, I could say, what is the polarity of the carbon-chlorine bond? It's polar. The carbon-chlorine bond is polar. But the whole thing is nonpolar.
So,
Now you got it?
okay, so carbon chlorine is polar because of the difference in the electronegativity, but overall they're all going in different directions, so that's why.
Opposite directions. That's why it's nonpolar.
Okay.
And that's the answer for both of those two. Yes. Yes. Other questions over these 2 pages? Other questions about this? Okay. All right, let me talk to you about the test, and then I will answer questions on nomenclature. First of all, this test format is a little bit different than what you've had on the first test. The difference is you have 50 questions, 2 points apiece. So it's actually more questions, but fewer points per question. Why? The reason it's like that is because we have covered a lot of material. But it all went together, if you kind of think about it. I mean, it all went together, but it was a lot of different little things. If you go back in your notes, just literally go back to the first day of notes. That first day of notes dealt with, we labeled the periodic table metal, non-metal, metalloid. Solid, liquid, and gas. Do you remember? So you will have questions simply something, to the effect of what is the, or it could be what is the state of the non-metal in group 17, period 4. Or it could be what is the only non-metal that's a liquid at room temperature. What is a metal that's a liquid at room temperature? Or is there a metal? I don't usually give yes or no questions, but anything that related to that solid, liquid, gas, metal, non-metal, metalloid, periods, groups, families, all of that, you're going to have at least 1 or 2 questions about that. And that was simply just practicing reading that periodic table. It also dealt with knowing your symbols and elements, which again, you were supposed to have learned those already, and that's been a big thing to have to keep up with, but you've used it in your nomenclature, so hopefully you've gotten those down pat. None of those are like worth a lot of points, obviously. I mean, it's some simple stuff looking at the periodic table. So everything is 2 points apiece. We went on then, if I'm looking at your notes, we went on and you did subatomic particles, protons, neutrons, and electrons. Someone, I don't know if it was in this class or the other class, emailed me, which I love, by the way. Nobody ever emails me, but it's nice to hear someone email me and ask me a question. But they emailed me and they said, on the sapling homework, I keep getting the mass wrong. And did you do it or somebody else did it? But you're with it. You're amening, huh?
Are you looking around that or what?
No. The person who emailed me did not give me the question number, but my response back to them was, look at the question, and if it gave you protons, neutrons, and electrons, then it's an isotope. How do you get the mass if it gives you protons, neutrons, and electrons? You add the protons and the neutrons. And they didn't get back to me, so I'm assuming my theory was right. So if you have protons, neutrons, and electrons given to you, then you determine the mass by simply adding protons and neutrons. We did this. We did this isotope symbol, several, like 6 of them, or 8 even. If, though, I don't give you protons and neutrons, or I don't give you the symbol and the mass, now if I give you the mass and I give you the symbol, you can figure out neutrons, okay? But if I don't give you protons or neutrons or the mass, then the mass comes from the periodic table, and yes, you round it like I said to round it. But I'm pretty sure the question that they were talking about, they gave you protons and neutrons, okay? I'm pretty sure. So look back at that question, and if they gave you protons and neutrons, then you just needed to add them. You were not adding them, you were going to the periodic table and pulling it off the periodic table, and if you remember, the periodic table mass is what? An average. And it was trying to get you to pay attention to that exact isotope. So you will have questions like that. You need to know hydrogen's isotopes. That is not very hard if you'll try to keep it simple in the sense that you know the names. Tritium, deuterium, protium. 2 of them are indicative of their mass. Tri means what? 3. So tritium, 3. Deus also means 2. So deuterium is 2, and then protium is 1, which is what the average is. So that shouldn't be too hard either. So protium, deuterium, and tritium, you need to know those hydrogen isotopes. I believe your notes went on from there into electron configuration notation. We talked a lot about the colors of the rainbow, and we talked about why the fireworks give off the color that they give off. You need to know that. You need to know when you see the color. I want you to know when you see the color. When do you see the color? When they fall back. Not when they're jumping, when they fall back, because the law of conservation of energy is true. Do they have extra energy to give off? Yeah, they have extra energy to give off, and the color depends upon the energy given off. Know Roy G. Biv and know which one's the highest energy. Violet is near ultraviolet. Tans hurt. Just remember it that way. Okay? If it hurts you, it's high energy. So from that point, let's see, we were doing electron configuration notation. It's multiple choice. So many times students think a multiple choice test that's over electron configuration notation and nomenclature is going to be a piece of cake. I want to tell you, this test is not as easy if you treat it in that manner and you think, oh, it's a piece of cake because it's multiple choice. In fact, my strong suggestion is don't even look at the choices. When it comes to electron configuration notation or nomenclature, do not look at the choices at all until you've solved the problem. And let me tell you why. Let me give you an example of why. Let's say that I give you, let me give you an example because this is one that I see students well, I may not give you an example there. We're locked up. All right, let's do it here. On electron configuration notation, I'm not going to write all this one out, but I'm going to do nomenclature on one. On electron configuration notation, I may ask a question. Which of the following looks like argon? And then I might give you, for instance, I could give you sulfide, and I could just say sulfide. I could say sulfur. I could say titanium. I could say magnesium. Which of the following has an electron configuration notation that looks like argon? What should you do to answer that question? Do the electron configuration notation for each of those. But don't sit there and look at the choices. In that case, the choices, you have to see them, but do it. Do what you know to do. Don't try to just skim through it. Do what you know to do. Some of these also, I may say, for instance, which of the following is the correct electron configuration notation? And then I'll give you 5 electron configuration notation choices. That's where cover it up. Cover those choices up. And just do the electron configuration notation like you know how to do it without looking at the answers. Then compare yours to that one and pick the right one. Because I can guarantee you I'm going to have choices on there that if you only look at my choices, you will second guess yourself. Because I will put what you could be thinking if you really don't know what you're doing. So forget the choices and just do it. Nomenclature is huge about that. Let me give you an example on nomenclature. This is an example of something that you may see. Diphosphorus pentaoxide. And if I say, give me the correct formula for diphosphorus pentaoxide, cover up the choices, do it, and then find your choice. But I'm going to tell you what I will probably do for choices. Here are some choices that I will give you. Those are some choices I will give you. Now, if you don't know why they're laughing, I didn't put the correct choice on there until then. if you don't know, if you just start looking at those choices, then here's what you do. You probably immediately knock that one out, I hope. You probably immediately knock that one out. But then you look at this one, and either you blame it on, oh, I've slightly got dyslexia, or you think to yourself, do I crisscross those or not? That's what you start thinking. So you'll start looking at these and think, well, I might crisscross. Well, you know what? That could be, though, because that's -2 and that's -3, so maybe she crisscrossed. I don't know. Do you see what happens? And you will do that. I know what you all do, because that's what you do. Instead, cover this up and just do it. Then uncover it and circle your answer and move. Because you will sit there and tear yourself up, because you'll make yourself think, well, did she really mean to put... Yeah, she did. She's trying to trick you. Okay?
And like with these, I think on the notes, doesn't it say with these you don't ever crisscross?
You do not. In fact, you just, that's what I'm saying. You just ignore this junk down here, because you know she's trying to trick me. You just tell yourself that. So you just cover up all that stuff and you say diphosphorus, pentoxide. Boom, I got it. I'm not even going to look at her junk. I mean, that's what you do, okay? Because you will definitely mess yourself up if you start looking at my choices. Okay? What else, or what other types of questions are you going to see? You are going to see, I didn't say this earlier, or I may have, but I didn't say it specifically. There will definitely be isotope symbol that you have to read. Okay, and that's, again, that's on your sapling homework. I think that may have been where the problem was on that one question, similar to that. So you're going to see isotope symbol. You will have VSEPR geometrical shape. There will be questions that will say something to the effect of, what is the VSEPR geometrical shape of, and I give you the name of a polyatomic ion or a compound, and the 5 choices are what? You know them. What are they? Trigonal planar, trigonal pyramidal, and tetrahedral. So there's going to be 2 or 3 of those. I'm not going to be hand grading anything, so how am I going to ask you to draw a Lewis structure? I will say, which of the following, this could be an example, which of the following is a correct Lewis structure for, and then I have drawings for you. Again, cover up my answers and do it. Then look at my answers. Otherwise, you'll start saying, well, that one could be right, or that one could be right, or that could be right. And then you just mess up, so just do it. I will also have questions that may say this. This is just taking your knowledge a step further. What, or not what, let's do it this way. How many lone pairs of electrons are around the central atom in da-da-da-da-da? Like, and I could say, for instance, how many lone pairs of electrons are around carbon in carbonate? 0, 1, 2, 3, 4. So it could be, what do you have to do to answer that question? You have to draw it, and then you have to look for lone pairs. You have to draw it and then look for lone pairs. I'm trying to think if there's anything on there just straight up valence electrons. There could be a question, just how many valence electrons are in such and such. You have to know that to do Lewis structures, but there could be a question like that, just how many valence electrons. You will definitely see questions on there that ask something about how electrons are lost or gained. Remember we went through that whole scenario 2 different days, at the end of class 1 and at the beginning of another? And I was talking about the whole purpose of doing all that electron configuration notation was get you to the point to be able to realize, for instance, like 10 loses 2 electrons to become 10-2, 10 loses 4 to become +4, where are they lost from, all that scenario. So all of that type, just putting all this together. As far as today, there's probably 2 or 3 questions about what we did today. So there's not a whole lot about today. And the other thing I am going to count for you, I'm going to tell you how many questions have to do with nomenclature. "13 nomenclature questions." That means 26 nomenclature points. 26 nomenclature points. And I'm actually going to turn this off because I do need to show you something if I can get this thing to work. And there will be one dimensional analysis question. Maybe I've just blown it up too big. So there will be one dimensional analysis question. Let me try one more time. I don't know why it's doing this. I want to show you the periodic table I'm going to give you. Scared to do this. There we go. Okay, let me show you the periodic table that I will give you on your exam. I am giving you a labeled periodic table. I know, isn't that ridiculous, right? Let me just add some silver to that spoon as you put it in your mouth. All right, so this is what I will give you. Now, I don't want you wasting your time or mine right now writing everything down that's at the top there. Instead, just simply write chromate, dichromate, oxalate, carbonate, acetate, hydroxide. You can look them up later. Just write the words down now. And then the perchlorate through hypochlorite. Just write that down and you can look those up later, but know that those are the ions that I'm giving you. And that I am giving you a labeled periodic table for electron configuration notation, although I really don't think you needed it because you all knew that. This is it. This is what I give you. Anything else you want on here, you put it on there. Go ahead, question.
So on sapling, whenever you do electron configuration?
You know, is there one on there that you have to use their periodic table because it messes it up down here? Is that what you're going to tell me?
No.
Oh, then I'll shut up. Sorry.
Order than we do. Instead of going from like 4s2 to 3d10 to 4d6, you have to do like all the threes have to be allowed.
That should not be.
Okay, so sapling's wrong. How we learn it.
I've never seen sapling be that way.
Like whenever you get them wrong, like whenever you type them.
Send me the question.
I got it eventually, but
Send me that question because nobody's shown me that before. And if that's the case, I need to get that question off there. Nobody has ever told me that. So send me that question that it is like that. Okay?
You said you're using polyatomic ions for nomenclature.
No, I didn't say that. I didn't say that. Her question was, so are you using these polyatomic ions for nomenclature? I didn't say that. I just said I'm giving you these. I didn't say these will be used. I didn't say these are the only ones that will be used. I'm just giving you these. That's what I'm giving you. And that's what I'm saying. Okay? You might get lucky. You may not get lucky. Question. I'm giving you 454 grams equals 1 pound. Can't tell you if it's useful or not, but that's what I'm giving you.
So when you say that you're giving us this information, when you give us a periodic table, like it's
I have copied this periodic table. I can't explain that any better. This is the periodic table you will get on your test. Okay? Wah, wah, wah. All right, now then, questions that you have. Guys, be quiet so you can hear the questions.
I think I know the answer on that anyway. So on the ones that are considered metalloids, and then you've got your little zigzag lines out there. All the ones to this side, if it's a compound between technically a metalloid and a non-metal, it's covalent, and then on this side of the zigzag, it's transitional.
On the left of the zigzag or the stair step, it's a transition metal over to the alkaline earth metal family.
Yeah, I just wanted to make sure because these are considered metalloids, right?
Correct.
I wanted to make
But
sure
as
that on
far as
compound-
our division in compounds, we don't call the metalloids anything except for the side that they're on.
Okay, I just want to make sure.
Yes.
And well, I have another one.
Go ahead. No, go ahead.
The ones like zinc, cadmium, mercury, silver, and aluminum that we know the charges for.
You do not use Roman
Okay,
numerals.
that's what I wanted to make sure.
You do not use, now, except for mercury, you do. Mercury is mercury 1, mercury 2, but it's still always plus 2.
So like.
So mercury, mercuric, and mercurous, and they're goofy. It's mercury 1 is Hg2, mercury 2 is just Hg.
Okay, that was.
They're goofy. They are goofy. They are goofy. What other questions do you have?
Technically, since you're having one-dimensional analysis, you need calculators.
Yes. There is a dimensional analysis question. So would you want to bring a calculator? Yes. Bring a calculator. I will not be giving calculators out. Non-graphing. Bring a non-graphing calculator, no phone. If you don't have it, you don't use it. Okay? No sharing calculators.
What did you say about mercury? Mercuric is plus,
Both of them are plus 2.
instead of mercuric would be like plus 1 going down.
Exactly. Mercurius is not, it's both plus 2, but in essence what you could think, look at your sheet. Look at the back of your ion sheet. Look at the back of your ion sheet and you'll see it. It's on there, mercurius and mercuric. I think if you see them and with your eyes, you'll see the difference. But they're both plus 2. All right, what else, guys? Guys, be quiet so we can hear the questions, please. I provide Scantron and the test. The periodic table will be attached to the back of the test. I'm trying to think on this exam. There is the back page of the exam has only 2 questions on it, and I think the periodic table is attached to that. So I'm thinking there's not a 100% blank page, but I will not let you use your own scrap paper. There should be plenty of room to write on the test. If you needed extra, I would find some for you. The only thing you will be allowed to bring into the exam as far as with you to the table will be a pencil and a calculator with no case. I'll provide everything else. I'm thinking it's not. I don't have any of the actual copy test here. I mean, I copied them double-sided. For some reason, I'm thinking that there are 7 pages and that periodic table makes the 8th. But I may be wrong. It may be 6, and then I don't know. But if you don't have enough room, just raise your hand during the test, and I'll bring you a piece of scrap paper. I'll try to bring some extra. All right, what else? Guys, you're not asking me any nomenclature questions. Have you been doing nomenclature? You feel comfortable with nomenclature? You've done more than just one worksheet on nomenclature, right? You've practiced and practiced, like there's a lot of practice on Blackboard practice, whole sheets. Run through them. Okay. Anything else? All right, I will see you on Wednesday.